If you just do it, it'll turn out okay. We were supposed to have this last week, but stuff came up, death in the family, and we had to delay it a little bit. Everything's doing fine now, but welcome to our after show of our Before Earth miniseries. If you have any questions, we're gonna do a quick recap real fast. But if you have any questions, ask them in the comment section in the live chat below. And if you use our link up above, the pin linked up above, your questions will get priority. But all questions are welcome. But anyways, before we go on, I'll let my two guests introduce themselves for those who may not know who they are.
I'm Dr. Tapioca Weasel, also known as Vandy. I'm Michael Vandegraff. I am a physicist. I'm not a cosmologist. I'm not an astronomer. But I am a physicist, and I've had a great time learning so much about the history of our favorite universe here before Earth. But I think the star of the show has really definitely been our good friend Landon Knoll.
Oh, thank you. Thank you, kind. I'm Landon Knoll, an astronomer, member of the American Astronomical Society. I'm a planetary scientist, which means I tend to study planets because to me, planets are really cool in more ways than one compared with stars. But stars are nice. And one of the things the cosmos appears to be really good at is creating planets, because on planets, you get interesting situations. They look beautiful and they have fun stuff happen, at least on this one and likely elsewhere. So welcome. And I say I refer to our favorite universe not because I'm a proponent of a multi-universe theory, but I like to state the positive, which is this universe, of all the universes I know, which is only one, is my favorite.
Well, without stars, your planets and your physics wouldn't exist probably.
Well, I mean, the physics could still exist.
Yeah. Although my colleagues refer to me as a short-sighted astronomer because they're the ones that they're doing stuff for the supernovae in a very distant galaxies and so forth. And we're only sort of limited to maybe 1,000 light years before you get kind of out of the realm of being able to detect planets. But that'll improve. We'll get better.
Actually, that makes me wonder, what is the most distant exoplanet that we have confidently detected?
That's a good question. Well, there is the of course the wonderful site that is the Exosolar Planets Encyclopedia, exoplanet.eu. If you go there, you will see the current catalog of the number of planets that have been confirmed by more than one thing. Right now, we have 6,618 planets that have been detected and confirmed. There's a bunch of ones that are probable detections that are being looked at that. And in that on that website, there are various plots and catalogs and tools you can look at, data links to see sizes of planets versus their orbit versus their distance and so forth. And so if you went on that stuff, I'm sure you could find the most distant planet that has been solidly confirmed. Again, there's things that might be a planet, but
the most distant one that has passed muster to get on this database.
So if you look at the plot of planets around the set, there's sort of scatter plots and other things you can look at for the catalog. But if we look at, let's see, the planetary mass versus orbital period, we actually want to know, let's say, planetary mass versus, let's say, calculated distance, right? The distance of the host star.
Yeah.
Let's look at that thing. And here we see the distance of the host star. The plot thins out at around, I don't see anything above. I mean, the ones are around 10,000 light years.
I was able to get a tooltip. I was able to get my mouse over the data point that's highest, and it says it's something. My mouse is blocking it, and I can't move it.
Oh, it's parsecs. So about 10,000
yeah,
parsecs.
11,000 parsecs is what they give. They only give two significant figures, and that is something XTE J1751-305B. A very, very
and if you look at the
memorable
massive thing,
name.
it's a big massive thing, so it might actually be a sub.
Yeah,
Like
like
a giant dwarf thing. But it gets pretty thin after 1,000 light years, and it gets really thin after sort of 1,000 light years. So
before we start, so real fast. So, but the furthest planet that we've actually sent stuff to is Neptune, right?
We've sent a probe past the dwarf planet Pluto, New Horizons.
All right. So before we start asking questions, you want to give a little recap about our 5-part miniseries?
Yeah. The Big Bang is a process. It deals with the process, not a single event. It doesn't deal with the origin. It deals with the process where the universe started in a very hot, dense state and transitioned to the state as it is today. Along the way, a lot of weird stuff happened. Really, really weird stuff happens in the Planck era and then the inflation era, and then high energy states where photons were keeping things radiation dominated, and then hadrons kind of condensed out. Think of like the pudding started stuff condensing out as the universe began to be less dense and lower temperature. Finally, hadrons. Finally, atoms, and then with mostly hydrogen, chunk of helium and traces of lithium, and then all of a sudden the temperature cooled to the point where you no longer had plasma, and the photons took off. You had the Big Bang flash, you had the dark ages, and then weird stuff happened with first stars and galaxies, which we're still trying to figure out. And then you started getting nebulas and other things forming, along with the super clusters and clusters of galaxies and stars and whatnot. And in those planetary systems, this protostars with planetary systems being seeded by previous stars that went supernovae or neutron stars that collided. And in our particular case, the model is about 4.8 billion years ago. There was a supernovae whose shockwave began to collapse a gas cloud, which in one of the nodules was our sun. And then 100 million years later, or 4.7 billion years ago, a second supernovae went off to hit us with even more good stuff. Our protoplanetary system continued to evolve, and out of that, one of the lumps was Earth, although Jupiter played a big role in essentially scooping up a lot of stuff, making the asteroid belt only have the dwarf planet series and ripping off Mars a lot. Mercury had its own fate, Venus had its own fate, but Earth managed to get hit by an object about maybe 1/6 its size. The resulting collision resulted in the current Earth-Moon system that is today.
Awesome. Anybody wants to check out our work? I put the link to our slides in the chat and then the description below. Check it out. You check it out and check and be sure to always fact check our work yourselves.
So I'd ask you, saying, are there things in that series that I skipped over a lot of stuff? Right? Are there other things you want to highlight, particularly from a physics standpoint?
Yeah, I would say that there is a very real way, and I think this is like the most true sort of statement, but which is that the Big Bang is still happening now.
Yep.
But we, us included, all of us, Landon, myself, and Delia, we will all also still occasionally like talk about the Big Bang as being more like about the early time. But strictly speaking, we try to talk about it as being the beginning of the Big Bang. It's the beginning of this period of expanding space.
Yeah.
And the nature of space and the fact that space expands, even though the things in it don't necessarily expand, like atoms don't get bigger because space is expanding.
Your
That
gaining
is,
weight is not due to the universe expanding, right?
yes.
You're getting larger, right? That's
Yes.
That's a different phenomenon.
The cosmology, though, and the role of space as a dynamic thing that obeys certain laws of physics, described best by the theory of general relativity, is it is really fundamental to what the Big Bang is and what modern cosmology studies.
Sure.
And that would just sort of be one sort of big idea that I would think that I would want people to sort of like remember, regardless of it. Like, you don't need to know Einstein's field equations. I could write down one of them. I think there's more than one. I never actually studied general relativity in like a class, so
Yeah. Tensors are for computers to solve, or cruel professors to force their students to try to recite, right?
They're so hard.
Yeah, but as I say, when I taught the relativity in high school, I basically said, hey, look, here's the matrix of these all the terms, everything's paired, everything, da 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 da. That's all you need to know. Put it in a computer and let the computer solve the tensor, because that's what computers are for. But yeah, I think the notion that the Big Bang is a process, it's a model, and that model fits very well with experiments. One of the things that physicists doing accelerators to create mini little spots of high temperature dense stuff and see what happens, right? Understand the physics. The assumption is the physics today and the physics back then are the same physics. We just create things like accelerators to create little mini things and see what physics does. And ironically, you're right, general relativity is very important to understand the equations of the universe. But ironically, it probably is also the quantum mechanical effects that occurred really super, super, super early in the Big Bang that is also important.
Yes. Whenever you see if you Google the Big Bang and you look at pictures, one of the things that'll come up, most of the things that will come up are going to be images and maps of the cosmic microwave background, and those maps they're focusing on the very, very slight differences that we see in the temperature of the cosmic microwave background when we look to different points in the sky, and we've been able to map that out very precisely. But one of the things that those maps fail to really fully show is that those are literally microscopic sort of variations to within it's the changes are on the order of 1 part in 100,000 on the large end.
Yes, and 100 billion on the subtle end, right?
If you had like I don't know the exact like analogy. We could, I mean, if we wanted to, we could sit here and calculate it probably on the fly. But if you had a ball the size of a tennis ball, you would be completely incapable without some fancy equipment of detecting a bump that size.
Yeah.
It was very uniform, but not quite. Not quite.
And that's part of. I'm suspecting quantum mechanics played a role. Typically in the universe today, if someone says, "I want something precisely," blah blah blah, quantum mechanics comes up and said, I'm personifying what quantum mechanics does, but that's the fate of stuff. Also, the Big Bang as a term came from Hoyle, who was born in 1915 on the 24th, I think, of June, and he was on a radio show, and he was essentially decrying this new-fangled cosmology because he wanted the universe to be a steady state, and he thought it was a pejorative term. I can tell you when he was he was a Russell lecturer for the American Astronomical Society. Even then, he was complaining about Big Bang cosmology and so forth.
Did you meet him?
I never met him,
Okay.
but I've seen the results. Russell lecturers are because they have famous people come and they're sort of like people like Fermi and so forth show up and give lectures, and he just remained. It's a sad thing. He didn't
curmudgeonly.
I mean, Zwicky was curmudgeonly, but he did it based upon data. Hoyle just didn't like it, and Feynman was really big on saying the universe doesn't have to please you; it does what it does. In fact, he would say, I think more importantly, he said the universe doesn't give a damn what you think; it's going to do what it does. Your job is to try to figure out what it's doing. So,
yes.
Oh,
real fast. We have two questions so far.
Sure. Let's talk to the questions.
Well, we should let Ness introduce himself.
Oh, sorry.
Oh, I'm sorry. Hi, Ness.
I don't mean to interrupt, and I deeply apologize, but I completely forgot about this.
Okay.
Sorry.
So this show is for our listeners to ask questions, and you're right on time to be able to start answering these questions.
Yeah.
Because as Feynman would always start off the lecture, his very first words were, "Are there any questions?"
Yeah.
And you better have questions. So I am asking the audience, are there any questions? Because you better have them, because otherwise
first question
we'll
is
ask you questions.
This is from Boy. I ask, what do you think about the Planet X? Is it real or just a hoax?
The people that push what they call Planet 9 are on the level, it appears, allegedly, of trolling, right? They don't call it Planet X, they call it Planet 9 because they like to promote themselves as being the Pluto killer. They're mad that
the what killer?
The Pluto killer.
Okay.
Because a person who detected Charon, the double planet that Pluto, double dwarf planet companion, and so then he tries to say, well, I'm going to find the ninth planet, and they have put forward data that is that if you're very generous and you assume the planet
is consistent,
give them time. However, there are plenty of other reasonable explanations as to why the data does what it does, including nearby stars, because there are stars that get actually quite close to our solar system. There are stars that actually enter even the edge of the Oort cloud and so forth. So that's not a common thing. Within the Division of Planetary Science of the AIS, their attempts to push that narrative is not met with very good rigor. I think finally, when the Vera Rubin telescope is operating with the LSST camera, that will put a nail in the coffin, and hopefully those people have something better to do. I don't think much of their now. It's a good question, but the way they went about promoting it and self-promoting, I think, is a sad thing.
Yeah, didn't they used to call Planet X like Nemesis or something like that a long time ago?
Oh, there's been all kinds of things, but the notion of, well, there's a ninth, when Pluto was the ninth planet, and now it's about the 115th planet.
For 10.
Yeah.
Because X is the Roman numeral for 10. I think that was part of it. But also it's mysterious and fancy and Star Trek.
Their so-called search for stuff is really, I think, unscientific, in my opinion. They take data and they try to justify funding search for stuff. Again, Vera Rubin's going to put the nail in the coffin of their set of this. Yeah, the likelihood that there's some super Neptune thing out there causing stuff to happen is possible, but it's not very plausible. And there are plenty of other more reasonable explanations as to orbits.
If I remember correctly, this Planet X or 9 is also like hypothesized to be a rogue planet that has been captured. I don't know.
But then you're getting into like the more conspiracy theory like parts of it. Landon
really?
was mostly addressing the still within the realm of some type of.
Yeah.
They're trying to do legitimate science. They might be doing it poorly, but they're sort of trying. What the rogue planet Nibiru sort of stuff. Like Nibiru, the word Nibiru is not in any respectable astronomical paper, as far as I understand.
Yeah, the last time I even heard of Planet X or Nine or Nemesis was during Sailor Moon season 2.
So rogue planet is a term dealing with a planetary object which is no longer orbiting a fusor like a star, right? And we know there are planets that get ejected from solar systems under that really poor conceived thing that the IU voted on, and those people who voted for it should feel ashamed. But under that old system, things that got ejected from solar systems ceased to become planets. That was ridiculous, and that was fixed to say, okay, if an object is essentially ejected from orbiting a fusor like a star, it becomes a rogue planet. And we've detected some. They're very difficult to detect. And we think
there are probably
lots of them.
Once. You can't really track them because they're so. My understanding is one of the main ways that you detect rogue planets is through momentary gravitational lensing as they pass in front of other stuff. Because if you just have a dip in the luminosity of a star when it crosses, that could be from a billion different things. You can't say that that's from a rogue planet. A lens, though, that is much less likely to occur. So we have detected, and there are some estimations, like there could be a lot of rogue planets, sort of just which are just planets that are not bound to any stellar system.
Yeah,
that makes sense. But the chaotic system of like solar system formation would it would
solar system orbits
yeah.
are chaotic, right? They're not. Solar system orbits are not stable,
right?
And there is a plausible chance, in terms of a few percent, that, for example, the planet Mercury can be ejected and become a rogue planet, given stuff. It's given the amount of time, it's more likely the sun going its giant phase. But that's
of course, wouldn't the planets further away be rogue planets before Mercury would?
Not necessarily. Because what actually happens is you get interactions where the orbits end up getting such the orbits become unstable, and you have it so that on every little orbit, Jupiter accelerates this planet a little bit further, and it becomes more and more eccentric. And then because it becomes more and more eccentric, it gets a little bit closer to Jupiter, and it gets tweaked even more. And then suddenly, one of the times it's orbiting around, and it gets whacked by Jupiter, and it just gets launched right out.
And Mercury is a fairly elliptical orbit. It goes from about 0.38 AU, where Earth, Sun is 1, 0.38 to 0.48, right? So it already has a thing. So the model is more likely is that there's a resonance between Venus and Mercury where it gets more and more elliptical, and then finally gets interaction and goes fling out to the.
So the fact that most planets have like more or less circular orbits is more like a selective bias. Like any planet that have a very eccentric orbit are more likely to be ejected eventually,
or at least have their orbit modified.
Right.
Yes, or collide or something. I mean, things that are eccentric or crossing other orbits eventually interact with those things crossing other orbits. We think.
And this is something that we see. If you look at more than just the planets show this to some extent. But if you look at all of the asteroids and stuff, and all of the moons of the planets, the importance of orbital resonances, stable versus unstable. There are certain like ratios of orbits that are very, very common, like the 2-to-1. The Galilean moons are the classical example, the Galilean moons of Jupiter. And there are certain examples that are unstable, and basically there are no examples in the solar system, because if you had such an example, after 10 orbits, it's gotten flung out into a different orbit.
Mm-hmm.
Yeah. And it's interesting, if you look at, again, the next solar planet, you plot, let's say, planetary mass eccentricity, orbital eccentricity, you'll find that there are some, while most of the planets are somewhat circular, you'll find that there's some things that are quite elliptical, right?
Yeah.
But we think, in general, things that are doing lots of orbit zone crossing don't last as long, but we could be wrong.
All right. Next question is it possible for space to expand faster than the speed of light?
Yes.
That depends on what you mean. I think so. Locally, that statement doesn't necessarily make sense locally, but between any two spots, can the space between them increase faster than the speed of light? The answer to that is very clearly yes.
Yes, and Einstein's equations don't prohibit space from moving apart. 2 points in space moving apart faster than light. It's if you have rest mass, you can't travel through the grid of space at c. And if you don't have rest mass, you can only travel at c. So, but the grid of space can expand to its heart's content and not violate.
I may have asked this question before, but does space expand uniformly, like the same rate everywhere, or like are some regions expanding slower and some regions expanding faster? Maybe. Do we know that if it's possible?
I'm not aware that we do know that.
We've been measuring this so-called effect of dark energy, and it appears to be somewhat uniform. It's not over space. It may not be so uniform over time.
And that seems pretty clear, actually.
Yeah, and that's not a problem because if you think of that era of inflation when back on, I think, episode 1, we're talking about weird
stuff.
That
would have been episode 0.
Or maybe it was 0. Well, we also talked about a 1 as well.
Well, yes,
inflation period.
So it's not perfectly uniform, basically.
Well, over space, I don't think we have good enough resolution to say yes or no.
We don't see we don't see variance in the direction we look.
Yeah,
we might see variance in the going back in time.
Yeah,
but it seems to be
it's not symmetrical with respect to time. At least we know it's it changes. The rate changes over time.
Yeah. And
there's local variance of stuff.
And we don't have any evidence that it's not symmetrical with respect to space as well. But I don't know that we don't have measurements that can measure the local expansion of space to a part in one part in 1 million. We don't have
some of the recent galactic survey stuff suggested again that while dark energy may have varied in strength over time, that it seems to not be so variant in space. What are some other questions people have?
All right. Another question about the 9th planet thing.
Yes, that is so. Some scientists do believe that the best explanation for the orbital statistics of some subsets of trans-Neptunian objects is best described by another large planet that has sort of shepherded those into an orbit. That has not convinced the rest of the community. They might be right, but it's not compelling yet.
It doesn't help by the fact that they sit and try to troll people about Pluto, suggest somewhat what their motivations might be. I'm just alleging that. It also doesn't help the fact that there are much simpler explanations for why orbits in the Kuiper belt, let alone Oort cloud, might be weird. The most obvious is that we have frequent stars that get close to our system and perturb things. And if you talk about something knocking stuff around and changing orbits, a star that grazes the edge of your solar system is a big perturbance thing. You don't need to then try to invent an excuse to get funding for a trans-Neptunian object. You can wait for Vera Rubin telescope and LSST to fire up and do a deep scan much better than you could do otherwise.
LLST or whatever you said. I'm not familiar with the specific.
LSST, the greatest camera that's ever been built, the largest refracting lens that's ever been made on the Vera Rubin telescope. LSST, the Large Synoptic Survey telescope.
Why
camera.
are they using a refracting telescope?
No, the camera is refracting, right? It's got a refracting lens.
Oh, okay. Right? But the main light collector is a reflector, I would assume.
Yes, the Vera Rubin telescope is a so Vera Rubin.
One of the most important astronomers and astrophysicists of all time, Vera Rubin. She was one of the people that she was the one that is, I think, most well identified, possibly with Zwicky, with identifying the galaxy rotation rate anomalies that were the first evidence that pointed in the direction of dark matter. She did her work, I believe, in the 60s and 70s.
Yes.
That big work. And
Zwicky was very critical of people ignoring her work because it was inconvenient. He was quite a champion of it. But if you look at the LSST camera, it was made by the Stanford Linear Accelerator National Laboratory.
Hey, that's down the street.
Yeah, LSST camera. You look up LSST camera in Slack, and you'll see this extraordinary camera. That's the primary camera photo for LSST. Beautiful. And that lens in front, the camera design is interesting.
Priceless.
This is a thing. I think it's I guess in, I don't know what it's in.
Wow.
In feet.
3.5 degree field of view. That's incredible.
Yes. And and it's going to be able to scan. So the Vera Rubin is going to be able to scan the entire night sky every 3 nights.
That's insane.
Extraordinary deep. It's an 8.4 meter refracting telescope. Entire night sky every 3 nights. The data comes up at 10. They're expecting that the data coming off of that thing is going to be it's a huge amount of stuff. I mean, it's going to be
entering
15 terabytes a night of data. It's going to come.
Yeah, that's a lot,
right? And they've got a set down. I think the actual refracting lens in front of the camera is something, I guess, it's nearly 2 meters.
They have a person standing next to it, and it looks like the limiting aperture is at least 1.5 meters, which is insane.
Yeah, I mean, because I think in feet, if you're in that thing, about 5.5 feet, across. And I've seen the lens, not on the camera. I've seen the lens, and it's an impressive thing because it's optical quality and stuff. It's an extraordinary camera, and I think it's quite fitting that Vera Rubin's name be on this thing, given the amount of hard work she did in slogging through a lot of data to give us some very important insights into the cosmos. So that's going to be something where I'm withholding the statement. It's unlikely to be a large trans-Neptunian object to be found. I'm not saying it isn't, but it's unlikely. Once the Vera Rubin starts scanning, if it doesn't find it, more reasonable explanations of people who are not Pluto trolls will probably stand.
As a transition to our next question, sorry if I stepped on your feet there, Vandalia, but we can't rule out the idea of there being a large planet far off in the Kuiper Belt, as well as we can definitively rule out that there is a proper moon around Earth. We do not have a proper secondary moon. We might have occasional captured asteroids, but there's nothing else that is big enough to coalesce into a sphere.
Yeah. As a fan things about that camera, so it's going to take a 15-second exposure every 20 seconds on this 3.2 gigapixel camera with extraordinary depth. The 5 seconds is we have to pull the data off the back, cryogenically cooled. One of the big challenges is how to get that much data out
Yeah.
of the thing
Fast.
without the camera heating up. But
Okay.
yeah,
But-
it's going to have 15 terabytes of data coming off every night. And it's going to be very important for looking for transients, like detecting planets from other stars. It's going to be very important to look for asteroids, particularly one that might have a name on it. Galaxies, all kinds of good stuff. It'll be great.
Like, speaking of this question real fast, going back to our last episode of the planet formation and stuff, how big does an object have to be before it starts getting spherical?
Oh,
It depends on
which
the
limit-
matter, right?
Is that the
material.
Hill limit? Is that what that's called? The Hill limit?
Yeah, it depends on the material.
It does depend on the material, yes.
if you
Water,
have-
for example,
sandy
basically
water
does it at all levels.
Yes.
Because
a rubble pile versus a iron object. So I think like Lucy is the one that
But
they're
what the
probe
cheese
is going
without
to
gravity.
that is a big metallic block. Might have pointy bits on it more than something like a rubble pile. It kind of depends on the size.
Yeah, but if you think about like just if you're thinking about a collection of rubble, which is probably the typical kind of thing that
Like planets
would be
and
an issue,
moons?
it has to be. Landon, you would know this better than I would, but I know like 1 kilometer would be too small.
Yeah, I think Sirius is kind of the dwarf planet Sirius, formerly known as a minor planet, but now they're called planets. Is kind of at the limit. For example, again, it depends on the material involved.
And like Phoebos and Deimos, the moons
Too
of
small.
of Mars, they are not large enough. If you stood on Phoebos and Deimos, and you like were able to run across and jump, you wouldn't be able to run because you would end up just doing hops.
I mean,
you could throw a baseball into orbit.
Yeah.
If you
the mean diameter of Sirius is around 940 kilometers. So as you get below 1,000 kilometers, it gets to be less likely and more likely to be lumpy. So somewhere in that region, there probably are smaller. There's 115 dwarf planets. I haven't memorized them all.
So unlike what
in our solar system, right?
So
our solar system has 115 planets.
Right.
And
So
I can remember a few
you
of
said
them.
that they're flat. So unlike what Fliffers think, those moons are actually are flat planets.
No, they're potato planets.
Oh.
Yeah.
And they're not planets
They're lumpy.
because I don't think there's any.
We'll take their moons technically.
Well, so that a planet. So Io is a moon, but it's also a planet by the actual proper definition of a planet, because a planet is something that is. There is a specific term for this, and I don't remember what it is off the top of my head. I think it's the Hill radius.
Equilibrium, right?
Yeah.
Or not?
Well, you have to. Like, yes, that's true, but that doesn't answer the question of like how large does it have to get. I don't think.
I mean, the term we're talking about is called hydrostatic equilibrium. It's the fancy name for it's got enough stuff to there. That probably radius greater than 400 kilometers would normally be in there. So radius 400 kilometers, diameter 800 kilometers, just kind of.
It depends on time
depending
frame.
on what it has, and it depends on what it's about.
And what it's doing and how long it's doing it. Because if it's just out in the middle of intergalactic space where there's never anything to ever break any symmetry, then it's not going to have the very small sort of stresses and strains that would eventually lead to it.
So one of my colleagues just mentioned me saying Orcus, it's a dwarf planet. It's probably the one that's the smallest. It has a diameter between 870 and 960 kilometers. So probably the answer is somewhere in the 900 kilometer diameter range.
Yeah, I see.
The typical stuff is kind of the set there. And it's and you look at stuff from the Hubble picture of Orcus, it's got a cute little moon going around it as well. So we know the mass very easily. It's a round thing.
Yeah, I
But
also see that there are like asteroids that are about 500 kilometers across, and they are not in hydrostatic equilibrium. So there's maybe a
Yeah.
transition point from 500 or between 500 and 1,000 kilometers, I think.
Yeah.
And it depends on the material.
And we're
Yeah.
talking about stuff big, roughly a spheroid, right? We're not talking about
Yeah.
round, right? And at 5 years old, I said the world is not round; it's lumpy. And what I meant to say was not a perfect sphere. There are lumps on it. It deviates from a sphere. But in fact, it's worse than that because we've got, it's a bulgy egg-shaped thing with a little bit of dent on the side. So when we're talking about something that's in equilibrium, it's roughly spheroid-ish like. But something like a sedna or something where you get weird shapes because it spins fast can change its how round it is.
I think it's you basically define its overall, like the dominant force that maintains its shape is gravity, basically the dominant force. That's how I would define it. Yeah. Of course, there are still exceptions, but yeah.
So what other questions we have?
Kate has a question. It says, "I hope it's a question or not." It says, "I hope this doesn't mean that the Big Crunch theory for the universe is not a possibility again."
The current data we have regarding how dark matter and dark energy are behaving suggests that a crunch is not likely.
Not likely.
Impossible.
It is possible. Yeah.
Yeah, but it's unlike now. The question is, will dark energy in particular continue to behave as it has before? Given we don't know really what it is, but if it behaves like it has before, it's unlikely that the universe will get back together in a nice crunch, given our current understanding. But people are. This is an open question. But you've asked a really good question, and people are asking that and trying to figure it out. But
on the other hand,
probably not.
Yeah. On the other hand, I wouldn't worry about it, Caden. In the unlikely scenario that there is any of us around to worry about those problems, we will have literally billions of years to figure it out. Possibly trillions. Or we'll all die before that for unrelated reasons, as one does.
Yeah. So question about planets have to be a sphere, right? Answer is from the geophysical definition of a planet, and you can look up on Wikipedia, geophysical definition of a planet. It's pretty straightforward. It says a planetary body is defined as any body in space that satisfies the following testable upper and lower bound criteria on its mass. If isolated from external perturbances, like the body must be low enough in mass that at no time, past or present, can it generate energy in its interior due to a self-sustaining nuclear chain fusion reaction. So it's not a fusor. Right? That's the one side. And it's large enough that its shape becomes determined primarily by gravity rather than by mechanical strength or other factors. Is in less than a Hubble time. So the body would, on that time scale, reach a state of hydrostatic equilibrium in its interior.
How long is the Hubble time?
Isn't the Hubble time the 14.4 billion years? It's sort of the kind of the extended.
I think so. I can imagine. I can't remember this, and I'll look this up after I finish my thought. I could also imagine that the Hubble time might be defined by extrapolating the current rate of expansion backwards.
And so
that would be a slightly different amount of time, but it would still be on the same order.
I mean, Hubble time is an arbitrary thing because it's assuming the current expansion, but that's how it's defined. So basically what they're saying is, given the history of the universe, the thing deforms into a roughly spherical shape. But it's not mass enough that's causing fusion to go on its core either in the past or currently. So
and it has to be solid.
It's a spherish thing.
What does it have to? Does it have to be a solid?
No.
There's
nothing that says about what it has to be made of.
Then in that
its
case,
shape has to be determined primarily by gravity rather than mechanical strength.
In that case, why don't spherical globular clusters, count as planets, though?
Because they are full of things that are fusing. Remember, the upper bound
That's
is low enough
a
in
good
mass
point.
that at no time in
Okay.
the past or present can it generate energy in its interior due to any self-sustaining nuclear fusion chain reaction. Now,
Okay,
if you're mean
you're
enough
right,
to set
right.
a nuke in the middle of your planet, that doesn't count. It's self-sustaining, right?
Well, it reminds me of something like I don't know how credible this is. I probably think it's not credible, but I've heard that some people are arguing that there is fusion going on in the core of the Earth, but I don't buy that.
There's
Yeah.
no good evidence for that.
And so planets are which orbit their star directly. Planet scale satellites, a largest being one of the things being our moon or Galilean satellites, orbit other planets. Unbound planets are rogue planets that have been injected from a system. Double planets like Pluto orbit each other. The common center in a minute. There's uber planets that are big enough that they basically grab and sweep out their orbit. There are ultraplanets, which are essentially things that haven't cleared their neighborhood and are probably going to be smacked by stuff. There's all kinds of qualifiers, right? Planet
Exactly,
is there.
and the lines between these things are not sharp most of the time. Sometimes maybe you can get a sharp one, but most of the time they're not going to be sharp. And our solar system is a really great example of this because of the diversity of the different sizes of planets. Like, everybody agrees that Mercury is a planet, and everybody agrees that Jupiter is a planet. Let me tell you, Jupiter is way, way more influential on everything else that's happening in the solar system than Mercury is.
Yeah. And so again, for them to say, yeah, but they declared planet Pluto, no, a bunch of idiots not following procedures of a group called the IU that likes to be self-important said, solely based upon orbital mechanics, that created this definition that only things orbiting our star were planets, everything else could go F themselves, right?
I also
it was
remember
repaired in 2018, where what the IU said was it's a substellar mass that's never undergone nuclear fusion, has enough gravitation round to the hydrostatic equilibrium, regardless of its orbital parameters. So in 2018, the IU came back and said, let's fix our stuff. And
I would prefer.
Pluto is a dwarf planet, a dwarf planet type of planet. So Pluto's a planet. So as well as 115 other objects in our solar system.
And I also prefer like that definition, because if you entangle the orbital mechanics with the geophysical properties, then it becomes a real mess, because those two are not correlated at all.
And so the planetary definition is based upon what it is, not where it is.
Yes.
Speaking of rounded stuff, Kane asks, I wonder if there are any more gravitational rounded dwarf planets in the Kuiper Belt or cloud.
Probably lots of them.
We
found 115 so far, and Vera Rubin's probably going to pile up.
Well, when you say 115, though, you're including satellites of other planets.
Our moon is a dwarf planet.
If we omit that, and discuss planets that are not that are not primarily, and that's the problem, is like all of these things are a little bit fuzzy, and you have to be more precise about them. But like Pluto and Charon are primarily sort of orbiting their barycenter is not.
There was called a double planet.
Their barycenter is outside of both of them.
Yeah,
it's a binary system.
That's a type of that affected a double dwarf planet because they're both dwarf planets.
Yeah. But Io is orbiting Jupiter, and that's not a double planet, but in that sense, because they're not orbiting each other.
Because the barycenter is
well within Jupiter.
Isn't there like a dwarf planet inside the asteroid belt too?
Ceres is in there.
Ceres is in there. So again, we have 115 planets of various types. There's the classical planets. That's a historical artifact. And there are things like the ultraplanets which haven't cleared their neighborhood, and there are other planets that are diametrically dominant. Although even Jupiter, right? It's got all those Trojan asteroids that are 6 degrees in front and back. They have tens of thousands of asteroids, which we're going and visiting with the Lucy space probe. So if you even the notion of clearing its orbit, Earth didn't clear its orbit. We got this big honking thing called Moon nearby, and Jupiter doesn't clear its orbit because it's got these things in front and back of it, tens of thousands of things. So that clearing its orbit is a property, orbital property, not a physical property. So
before we get to the next question, I have a question my own, and that is, how did we find out that before? How can we phrase this? How do we find out, or when did we find out, or how, when, whatever, that this that the what we call the wandering stars were planets, the stars that moved all weird like?
So how did we find out that those are? Well, I'm going to reword this to be a little bit more precise, and tell me if it still captures what you're talking about. How did we discover that they are relatively like nearby and smaller compared to something like the sun, and so that they're sort of orbit, they're in like a local neighborhood of some sense? Is that what you mean?
Yeah, something like that. We thought they were weird stars at first, and we found out was that
points of light that move, right? And
if you define star as a light in the sky, then it is a star.
Yeah, although the sun and the moon were weird because they're disks and not points.
Yes, and this is because this is back when we thought the planet was the center of the universe still.
And people that didn't think Earth was a planet.
Well, also the question of whether Earth is the center of the universe. I mean, Earth is the center of the universe as much as any other point is.
True.
But there is no center. There is no center.
Because the word planet is a Greek term meaning wanderer, right? And so people didn't think Earth was a planet because it wasn't wandering; it was here, right? And that visible points of light to antiquity said the sun, the moon, Mercury, Venus, Mars, Jupiter, Saturn. Right? So sun, moon, Mercury, Venus, Mars, Jupiter, Saturn were the points of light that wandered. Earth didn't wander, so Earth was not a planet. They didn't know about Uranus, Neptune, Pluto, and other things like that. Yeah. They don't detect visible stuff. So sun, moon, Mercury, Venus, Mars, Jupiter, Saturn were wandering points of light.
Yeah, but they weren't. But unlike the sun and the moon, they weren't circling around us. They had a weird.
Well, they didn't know that because we didn't see circle around. We saw these things going wandering back.
The retrograde motion, and retrograde motion was one of the big puzzles that the first time somebody sat down and like solved it and figured it out, I guarantee you that person felt extremely smart, probably for the rest of their life.
Yes,
and they should.
And that's why we found out that we're around the sun, not the sun around us.
Yeah, and so Tycho Brahe and his data and Kepler, and then coming up with the notion of ellipses, not circles, and then Newton saying, calculus, blah blah
Newton
blah,
putting a model to it. Yeah,
Newton,
because that's what Newton did. Newton put a model to it, but the work of Brahe and Kepler cannot be overstated. Like because Brahe took incredibly voluminous, good measurements, and then Kepler was able to synthesize this massive
and Kepler was an assistant
of data
that lived up to Brahe's requirements for visual acuity, right? And they did lots of data there to come up with this thing. Now, it wasn't until the use of telescopes that people looked at what was originally a point-sized object of like Jupiter and say, oh, it's a disk thing, like the moon, like the sun, and Saturn was a disk thing, although it had this weird stuff around it, which turned out to be the rings and so forth.
And Jupiter had a disk, but then it also had the moons. But those were resolvable even by the very earliest telescopes. That's why they're called the Galilean moons, because Galileo.
Although he didn't fully get those things because again, there's a simultaneous detection of stuff where while we give the Roman numerals to the thing and called Galilean moons, it was actually they were discovered what's his name? I should know this. The person, the discoverer of that he gave us the names of stuff because Galileo would have named it after the Domenici family.
I gotta make a joke real fast. Speaking of Galileo, it's a good thing religious people aren't against science anymore. Like they were with Galileo.
Yeah.
Thank God.
But I think I'll get his name in just a moment.
While you're looking it up, see real fast. The next question.
Oh, Simon Marius. Simon Marius actually beat Galileo by a couple of days to discovering moons. Galileo was not the first person to use a telescope to look up in the sky. He was one of the better ones.
Katina has a question.
Yeah.
Could a star go cold? Yeah, that's it. Yes.
Could a star go cold?
I think like a white dwarf. A white dwarf.
Well, white dwarf becomes a black dwarf.
Technically, well, but think about the definition. Oh no, it doesn't satisfy the requirement that at no point in its past did it have a sustained nuclear reaction. So no, because it's retroactive. The definition.
And so a white dwarf cooling down becomes a black dwarf. There have not been any black dwarfs that the Earth hasn't been around long enough for us to find really cold.
I don't think they exist yet. Yeah, I don't think they exist yet. If they do exist, and we find some,
that'd be really interesting.
That would be extremely interesting, and I think would require it would either require new particle physics or it would require new cosmology.
Yeah. Look up the name Simon Marius, Marius. He was a really credible German astronomer who beat Galileo to discovering of Galilean moons and other things like that, and had his dispute with Galileo over who had the rights to what. A pretty interesting dude, Simon Marius, Marius.
Yeah.
Anybody else have any questions, or while we're waiting for questions?
Oh,
you guys want to talk about any questions you might have and stuff, or discuss some points?
Didn't the chat have other questions?
Not currently.
There were. If you scroll up, I'm pretty sure there were. But let me see if I can find any. Caden asked this question earlier, and I said it was a great question. Can rogue planets actually get caught within the gravity of another star and get drawn into orbit?
Yes.
And the answer is yes. One way that you could see that is we described earlier how when you have more than two planets, then you have a chaotic system. If you have more than two orbiting bodies, that system is chaotic. By which I mean, if the initial conditions are even vanishingly small different, eventually the evolution will go in completely different directions, and you will have no predictive ability to compare after a long enough amount of time. And those systems, normally what you have is you'll have a big central planet, and then you'll have two other planets, and they're orbiting, and they kind of slingshot each other around enough, and then eventually one of them gets launched out.
Yeah.
That same process can happen in reverse.
Yeah. And also the orbit that gets ejected, they tend to basically come back in. So they get it's likely that a rogue planet will be tossed out of a galaxy. It probably orbits, comes back into the galaxy, and then gets caught eventually.
Yeah,
it's more likely given dynamics and stuff.
Typically, it has some chance of doing that, but not always. It can get enough energy just to sort of get that's what happened with Voyager. With the Voyager spacecraft and with New Horizons, right?
Yeah, and so dwarf planets or dwarf galaxies are going to have more extrasolar galactic rogue planets as opposed to galactic, between galaxy rogue planets. And so most likely you're going to find most of your rogue planets in the halo around a galaxy that's big. Smaller galaxies, dwarf galaxies, will probably can eject it, easier to eject. But yeah, it's a dynamic thing.
Oh,
So
I had a question about like
Sure.
can moons have their own satellite? I'm not aware of any
yes,
like that in our solar system. So maybe they are unstable. I don't know if there are any in our solar system.
Not aware of any.
Yeah.
I'm not aware of a so-called moon of a moon.
Yeah.
The natural one, at
There
least.
there
You'll-
are, but there's nothing that prevents it from happening. It might
And
not be
the only
very
yeah
stable.
the only and like this could be wrong, but the only satellite of a planet that is the primary satellite of the sun that I'm aware of are going to be natural artificial objects rather that we put into orbit around our moon
Right.
or around
But-
potentially any other
Uh,
planets if we have
I-
those. I don't know if we do right now.
Like real fast, one of the questions. I confirm something. Dwarf planets aren't called dwarf because of their size. It's because there's stuff in their way of the orbit. I think.
So, by the way, the name for what you're talking about is submoon, and
Oh.
and the general thing is that they're not dynamically stable. So, if you have a
Yeah.
submoon, it's suspected it won't last very long.
Well, I meant like Pluto and Ceres and stuff. It's because there's stuff in the way.
Pluto is a stable thing, right?
I heard somewhere that's because there's stuff in their orbit path or something.
Yeah,
The
so
reason
you're
why
talking
they are
about
called
clearing out
dwarf.
the orbit.
The reason, like Vandal is asking why they are called dwarf planets specifically. Like why are not like the difference between a planet and a dwarf planet?
Is that because the size, right?
It also has to do with whether or not they've cleared their
Yes,
dominant in their orbit.
Yeah,
Like
that's what he's
Uber
asking.
versus Unter planet is a distinction there. So all right, but back to we should also get some questions, audience, about the Big Bang process or about how Earth Moon formed or something like that.
Hey, Maya. Yeah, Maya, do you have any questions about the universe? Our solar system?
About the Big Bang process, about how our Earth Moon system formed, stellar evolution, galactic evolution.
Okay, is a James Webb Space Telescope still active? Have we learned something recently from it?
Yeah, yes, it's still active. Let me tell you, that thing's going to be active until it dies a cold, hard death, and all of the people that they can hire can't figure out any way to revive it.
It's very healthy. It is very productive.
It's astonishing.
The fact that it works is a testament to the engineers that did a good job. So thank you, folks.
And it works well. It works well. This thing, it came out of the box after 6 months of calibration, because that's how the box works here, working and surpassing every metric that they had as its sort of like requirements.
Yeah, and the fact that we're getting like spectrum of atmospheres around planets around other nearby stars is like phenomenal, right? It's
game changing.
And the fact that they were able to like find, although it has to show up for peer review, what appears to be a galaxy that's formed around when the Big Bang process was only about 400 million years old. If that holds up a peer review, is interesting, right? It's giving us insights into the very early end of the Dark Age.
Real fast, we get to my question. Did you know that only 32% of your viewers are subscribed to this channel? What's up with that?
Yeah, and could you click the like button, the little thumbs up thing, because it helps his channel.
Yeah, we're gonna need you to do that. We're gonna need you to smash that like button, and we're also gonna need you to subscribe, because guess what? It doesn't cost anything.
Yeah, and it's free, and it's a good thing, right?
Maya has a question.
What is the answer to life? Not 42. So you are not allowed to cheat.
69, Maya. Come on. That's an ill-posed question. And when you say, what is the answer to the universe? Also an ill-posed question. You got to be specific, Maya. Give us a question about inflaton theory or something.
A question also is that does the universe have an answer, right? Is it this begging the question? does the universe have any obligation to be explainable? That's one of the things that Feynman would challenge me on was, what makes you think the universe has to make sense to you? Because I was objecting to the weirdness of quantum mechanics, and quantum mechanics is weird, but it's also marvelous. And it's like, yeah, but blah blah. He says, "Well, the universe doesn't care." In fact, he was. I'll keep it PG. He said, "The universe doesn't give a damn what you think. It's going to do your job is to figure out what it might be doing."
Man,
like
I'm so jealous. I wish I had met Feynman.
He was cool, and he really liked play D&D and played drums and was had trouble with authority. He had problems with authority.
Yeah, he did. I have a number of his books, and some of his anecdotes about like his shenanigans during the Manhattan Project are genuinely horrifying on some level.
Yes, of stuff that I was doing. But he started in terms of some of his stuff. He talked about how, like, one of his hacks, he said, the sensors. I was communicating with my wife, and you couldn't make anything that would potentially dwarf it. And so they weren't interested in that, but they're interested in tweaking the sensors. And so one of the times he had his wife write an essay on a blackboard in, I think it was a foreign language, of obscure foreign language, and then cut up the cardboard into a puzzle, 1,000-piece puzzle, and stick it in a box, because you had to go through the sensors, and the sensors had to try to assemble this jigsaw puzzle to see that there's nothing in it that was there. And why? Because he could, right? On the other hand, he was pointing out that they were storing secrets in safes that didn't even have the default combination changed.
Caden asked, could a working theory of quantum gravity allow for the potential of FLT travel and artificial gravity being things that we potentially access?
Faster than light travel, FTL. Could a working theory of quantum gravity allow for the potential of FTL and artificial gravity being things we could potentially access? Depending on how you describe artificial gravity, you can already access it pretty trivially using like a centrifuge. The general answer to your question overall, I think is yes, but mostly because it's somewhat vague. Because a working theory of quantum gravity, it depends on what you consider falling within that description. And frankly, I'm fairly amenable to the idea that any explanation that both reproduces the explanations, the predictions of quantum mechanics and quantum field theory, and the predictions of general relativity, I would consider that to be worthy of the name quantum gravity. And that might totally upend things in ways that we can't predict.
Now, I am not convinced that gravity has to be quantum.
I'm also not convinced of that.
And it has, but remember, has to be quantum, right? So the notion
quantum?
that there must be a quantum, there must be some merger between quantum mechanics and relativity, is a desire, not a requirement.
Yes, that is true. There does have to be, in my opinion, some sort of resolution and explanation for when the predictions become diametrically opposite of each other.
Yeah,
because that does occur. That explicitly does occur when you actually compute things, but you're computing them then in a regime where you don't have access to any experimental data. But it does not, I would agree, it does not necessarily have to be quantum. There was a recent theory that I remember, Sabine Hossenfelder. She was describing a model that a colleague or a friend of hers that she knows has advanced, where there was an explicitly random element introduced into general relativity. And I didn't review that. I have no idea. I'm not the person to ask. But the high level explanation, I was like, I mean, that's a neat idea that I've never heard before.
Yeah. And I think Stephen Hassenfelder has some really good insights into physics there. I think my praise of her is I believe if Zwicky had met her, Zwicky would be satisfied that she was not a spherical asshole. Now, let me explain.
Please.
Zwicky was got to be pretty upset at his colleagues who ignored Vera Rubin's work and was trying to rationalize away the missing mass, which we call dark matter. And at one point in a Caltech faculty meeting, he stood up and says, "You're all spherical assholes." Now, this is Caltech, right? We're talking about some pretty important folks there. And the kind of explanation, he says, "Well, you're assholes whenever you look at you, so there must be spherical."
Amazing. That's an amazing burn.
But there were people for which he had high respect. I mean, von Neumann, Feynman, Rubin were people that he had high respect for because they didn't just go along the line. And Hassenfelder is a lady who does not simply go with a convenient explanation. Now, we should add, I do want to answer the FTL question, but that's just a little something or other. So, but back to what you were saying.
So, what's the difference between technical question? What's the difference between quantum gravity and regular gravity?
Okay, so in quantum mechanics, let me use vernacular, not mathematics, right? That you can't say this is where the electron is, right? We say quantum mechanics says no, you can't say it's precisely here. There's a probability cloud, right? In fact, the particle can actually be in multiple places at once, right? An electron, a thing you think is kind of a pointy bit, can go through two slits and interfere with itself. It goes through both. It's not just decides, it goes through both and then does wave things. It's really
because
quite
it
weird.
Is a wave. It's an inherently quantum mechanical object, and it's described by a wave equation.
Okay, so hear me out here and follow this along. So now an electron is really it's not really any one place, right? Now let's talk about, does electron have mass? Yes. Does mass warp space? Yes. So if this is an electron, the gravitational field would say, there it is. What happens now that's no longer here? It's in this probability cloud. Where does gravity field point, right? And how does, if you collapse and interact or quote measure, whatever that means, the electron and the wave function collapses, what happens to the gravitational pull that the electron had, right? These are questions people are asking that become really important at the extreme level. So the business I had with Hawking about his Thorne Hawking Pascal bet, the so-called encyclopedia bet, and really the debate I had was did Hawking give up his bet too early, right? Because is it true if you follow quantum mechanics to its extreme, Hawking was wrong and information is conserved going into a black hole. But is it? Right? If you're a quantum mechanist, you'd like to say yes, because if it isn't, quantum mechanics has big problems. Go ahead.
Quantum mechanic. Sorry, it's quantum mechanic, not quantum mechanics. Just like it's car mechanic and not a car mechanic.
Quantum mechanics, yes.
We're exactly. So it's all of that. It's sort of like the when we refer to like a classical theory, we're referring to like you've got like a block and the block has like a size and it's in a spot and it has a speed. All of those are perfectly well defined to any accuracy that you can conceive of. It's at a particular location and it's moving at a particular speed. And in quantum mechanics, it's not at a particular location. That same electron can be all over the place. And it's not moving at a particular speed either. It's sort of moving in a kind of a range of speeds. And that doesn't work with predictions explicitly of how,
Sure.
how the grid of space is being affected by mass. And you can do math that like it takes both of those things seriously, and it comes to certain conclusions, and those conclusions are either mathematically absurd or explicitly falsified.
So the thing is about the Feynman path integral, right? When quantum electrodynamics, when you talk about something going from here to yon, you have to count for every possible path, including from here to there. It doesn't go here to there. It goes out to Pluto, orbits 17 times, goes by Jupiter, decides to take a gander over to Saturn, comes back to Mercury, and then back to this spot. That is a valid path that must be accounted for in the path integral, right? And unfortunately, a lot of those really absurd things, which are technically possible, cancel each other out, and you get the more rational bit in between.
Yeah.
But it's a set. So faster than light. Relativity, again, if you're being precise, right? And this is something that was a big thing of don't be sloppy in your language. Math is probably the better way to describe it, but let me give you an analogy in words. Relativity says if you have rest mass, you're standing still with respect to some observer, and you have rest mass, you cannot go a speed called c, which we commonly call speed of light in a vacuum. Now, if you're going, you're happy to be going faster than c, faster than light already, you can go even faster, your heart's content. The problem is, how do you get faster than the speed of light without going the speed of light? So it's like saying, if you are going 50 miles an hour and you want to go to 100 miles an hour, some point you have to be going 75 miles an hour. And 70 miles an hour is the physics says no, you can't get from slower than the speed of light to faster speed of light before at some point going the speed of light, unless you've got some quantum mechanical weirdness where measuring the speed is not quite, and you can kind of fuzz your way across that barrier.
Yeah, or you can tunnel.
The problem is going things that have mass going c. Maybe they can fuzz their way across, just like things can fuzz their way out of a black hole event horizon. Maybe. So the answer to your question is maybe.
Yeah. And it also you can move from one location to another location faster than the like trajectory that a photon might take to there, but that's a trivial statement because it, like, if you have the photon bounce off a mirror, like, it can get there. You can make short, like, wormholes are things that are mathematically consistent with relativity. The formation of them and how you would go through them, we don't have any good idea on how that could possibly happen without just obviously killing you. Sure. It would probably obviously kill you because it would be microscopic. But moving through space locally faster than light, the thing about the speed of light is calling it the speed of light is short selling it. It's more like the speed of causality.
Exactly. Yeah.
It's the speed of causality.
And things that don't have rest mass can only go c, and things that do have rest mass apparently cannot do anything, cannot go c.
Yeah.
So generally the argument is if you're like 90% C and you go to 200% C, at some point you have to go through C, unless there's some weird quantum mechanical fuzzy thing that allows you to like tunnel across speed, and I don't know how that does, but who knows, right? My response to can you go faster than speed of light is I don't understand the physics that allows it. I never say it's impossible. I just say I don't understand the physics that allows that.
Yes, I totally agree. I think that it always bugs me when physicists say like no, when they're absolutist in their language. And
Yeah.
in my opinion, the best science communicators have been very good about not doing that. Like Carl Sagan was very, I feel like, open generally in his rhetoric. Maybe
Nice.
there would be nitpick things. Neil deGrasse Tyson, I've got a lot of issues with him, but he's pretty, honestly, when when push comes to shove, he articulates my sort of philosophy generally pretty well.
So
Although I
Wait.
have seen one criticism of Neil deGrasse Tyson in contrast to what you said about Carl Sagan.
Sagan.
Like when you listen to Carl Sagan makes it clear that you could like look into the universe and explore everything and always end up being surprised for an eternity. You always discover something new that surprises you. But Neil deGrasse Tyson is more like, follow these rules and the universe is yours, which is a very different message in my opinion.
And I know that Dr. Tyson has his comedy shtick, but he needs to get over Pluto being a dwarf planet. That being said, also people I've never met Sagan, but there was a number of his colleagues that didn't think he was a very nice person.
Wait. Hold on. Are you saying all scientists aren't all agree of everything? Aren't all a big collective agreeing of everything each other?
Yeah, I mean,
thing?
someone like
Have you
Zwicky,
met me?
someone like a Zwicky got testy when you were having fuzzier thinking or you were ignoring stuff because it was not convenient. That would drive him bonkers, and he would let you have it, right? If on the other hand you were honest enough to say I don't know, he would congratulate you for being scientific. So I don't know what the physics would allow you to go faster than speed of light if you have rest mass. I don't understand the physics, but it's worth exploring. Now, things like wormholes. One of the challenges are keeping a wormhole open long enough to do anything with it. The other challenge is a wormhole doesn't get you jailed free because you gotta like get both ends. If you get both ends, you're already there. So what's the? It's more for the Vogon doing this interstate space bypass to wipe out.
Yeah,
Earth.
and I still think that's extremely valuable. I like
wiping on Earth. You said wiping on Earth.
No, having like a bypass, like even if you still are limited by sea in getting to the place, establishing a connection that's a shortcut, that's still a game changer, right? Like,
and also the notion, some of the warping space stuff that requires negative mass. I don't understand negative mass or negative energy. There are people trying to fix that.
And antimatter falls down. By the way, we checked.
Yes.
We only figured it out in the last year, but it took a while.
Yeah, but negative mass would just be weird. It would be. I think there would be some really bad things happen. Now, the other big thing about going faster than the speed of light is we've never observed the universe doing it. If we could see things going zip, 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 that might give us some notion. Now, you might say, yeah, but if you go faster than speed of light, you can't detect it. Like, that's getting a little bit too silly. So I wish the universe would show us examples going faster than speed of light, because then we would have a better chance of trying.
Al Tucker says, according to Flores, Tyson is our Pope.
I would choose Feynman as my Pope way before Tyson, and I would choose Einstein probably above all else.
Yeah, Einstein. Although Maxwell, Einstein would say Maxwell, right?
Einstein would say Maxwell, but I think Maxwell would be like, yeah, well, you're being nice and you can't choose yourself because you're a nice. But Einstein was Einstein. I am on record, and if I'm not already, I'm here on record saying Einstein is underrated and deserved more Nobel Prizes.
Yes, and the fact that there were people on the Nobel Committee who accused Einstein of practicing Jude physique.
Oh,
will tell you why when it
Yeah.
Because when Eddington did the experiment and essentially said there's something to this warping space, Einstein deserved a prize for relativity, right?
Yes.
Ironically, he got it for quantum mechanics. We did a lot of good stuff because people don't realize how much important Einstein was to quantum mechanics, right? He's not an enemy of quantum mechanics.
They don't appreciate that. Einstein had a better understanding of quantum mechanics than all but maybe 10 other people on the planet at all points in the existence of quantum mechanics when he was alive.
Yeah. Now, I think however, the people that I met, I never met Einstein. I think the person who I said had the greatest sort of intuitive understanding of physics was Feynman. His intuitive grasp of physics was extraordinary, and his ability to ask the right question, the right person, at the right time. So,
before I forget about it, like you mentioned a few minutes ago that antimatter falls down, that we observe it fall down. It reminds me that in Feynman diagrams, antimatter is depicted as traveling backwards, right? Or am I mistaken?
No, the arrow designates it as a symbol, right? Because you're using the Feynman diagram to do your path integral combination order stuff, right? That's what the Feynman diagrams are for.
So from the perspective of antimatter, it is falling upwards, basically. If you flip the time around, basically.
But the Dirac, I think I'd much more comfortable with Dirac, who's another seriously smart dude that had big impact on our understanding of reality. It is a mathematical analogy, not necessarily reality.
It's not like antimatter from the perspective of antimatter. Time is not reversed, basically.
Yeah, because when a photon turns into an electron-positron pair, the positron isn't coming back from when it gets annihilated; it's going forward.
Right. But the arrow points backwards because it's like
the Feynman diagram is part of how you do the purpose of Feynman diagrams is to do your path integral combinations correctly. It was a trick.
Yeah.
It was a mnemonic.
It's a heuristic, but if formalized, it's a formalizable heuristic, and it was shown to be mathematically equivalent to the more direct sort of calculating approach of doing quantum mechanics and stuff. That was I always have was it Schwinger?
Yeah.
Yeah.
By the way, another person you said about a scientist, I would say Laplace was a person that I hold in very high regards. I would sometimes give Laplace a bit of edge over even Newton for somebody who his impact on physics and was kind of responsible for some of the stuff that Maxwell did, right? In that sense.
Real fast. So being a scientist and stuff. So who was the first scientist or observer that started this whole learning about space journey? Who?
Space journey?
Who was the first one that
what is space journey? Help me
I don't know.
The person who started thinking about space and trying to do science and make a model and a hypothesis and make theories about the heavens.
Well, Giordano Bruno was one of the early scientists who speculated that the dots in the sky are stars like our star, and they had worlds like our star had around them. He was an early proponent of that. Unfortunately, he also went theological, and was a Catholic priest who said, well, if these stars in the sky are just like our sun but farther away, then they have planets and they have salvation and they have God stuff, and they burn him at the stake for being a heretic. They actually purified his body by lighting him on fire. Now there's a statue there in Giordano Bruno Square in Rome where they said, sorry about burning you with the stake. That was a mistake.
Yeah, why did say I think why was I think it was the Aristotle theory about space last for so long?
Because some people said this person must be so smart that he must have to be divinely inspired. So they equated his ravings and his postulates and his guesses as being divinely correct. And to challenge it meant you were challenging the authority of the church, and challenging the authority of the church was considered naughty.
And everything was just a lot more localized then. People didn't have libraries to go to, let alone the internet. They didn't have libraries to go to. If a person wanted to go and find something that is up to date within the last 50 years of the state of the art, within the last 50 years, I'm being generous, it would take them a month, maybe, to do research to even like figure out where to go. And then they have to end up in like Alexandria, Egypt, or in Athens. There's like a few places. So everything was just so much slower. And so they didn't have any other, they didn't have any better heuristic than to just be like, this Aristotle guy is really well respected by everybody that we've ever met in the last 500 years.
Yeah.
So that seems good.
Yeah. But yeah, look up Giordano Bruno, Bruno. His life. He was one of those thinkers well ahead of his time. And unfortunately, he was also in a political situation where
he was in Rome, right?
Yes. And he and I believe, his cause of death was execution by burning at the stake.
That sounds awful.
But they wanted to purify his soul. But yeah, he was tried for heresy. Anyway, but he had some very interesting thoughts on there. So back to the business about, in questions. As I mentioned before we got on the air, one of Feynman's questions to me was a quite serious question, but I already thought he was joking. He said, "Why can we not remember the future?"
It's a real question.
Why can we not remember the future? What's with that, right?
And my response,
go ahead.
So my response was that question can like mean a lot of things, but the big flashing red light one to me as like a physicist is, why does time go in one direction?
Yeah.
It means more than that, but that was how it struck me when you said that. And that's why it's not just a silly question. Why can't we remember the future? Because it hasn't happened yet. What does that mean? That's what Feynman was getting at, right?
Yes. It's also like on the Feynman diagram, if you flip the time axis around, then all you do is you turn the matter into antimatter, and the antimatter is turned to normal matter.
Yeah.
Like it's symmetrical, basically.
But just because it's mathematics there doesn't mean that it's real, right? So it's a causality is part of the issue, right?
But there is like
does a cause always? Why does a cause always precede its effect?
But at the quantum scale, there is time symmetry, right? Like there is like if you basically if you play the movie quote unquote backwards, there is almost you cannot tell the difference between forward or backwards in time, right? Or
Or
am I mistaken?
Again, just don't put too much thought into the arrows in a Feynman diagram. It never implied these were going backwards, right?
Oh man, but I'm also talking.
Here's the thing: an energetic photon that breaks into an electron-positron pair, and they annihilate each other. Like the positron gets annihilated. It didn't go backwards. It went forward in time. It does go forward in time. The cause of the photon turning into a matter-antimatter pair by Lindsay squared, and the positron being annihilated is a cause effect. It's not backwards.
But if you were to view the scale, the quantum scale, if you were to view the process forwards or backwards in time, it looks the same, right? Like there is.
Yes.
Yeah.
It probably suggests that our mathematics, if it really is, if there is truly an arrow in time, our mathematics may be incomplete.
It actually it actually works with the mathematics fine. The thing about it is that you have an established like initial condition, and then when you evolve that, it like does stuff, and it the arrow of time ends up being sort of emergent.
Yes. That's also
But
the point that I was trying to make about. Yeah.
Yeah. If you, but that doesn't change the fundamental like validity of the question. It makes it a little bit harder to quantify in a clear physics manner that maps onto what we're getting at. Because what we're getting at is a way more complicated thing than it can be explained by a single equation.
Like I've heard that the arrow of time is basically related to entropy. And entropy is like an emergent phenomenon where you have like lots of matter in aggregate, then you observe entropy, basically, right? Yeah.
Yes, entropy is an emergent property of a whole lot of matter, but the more fundamental thing is causality, and causality doesn't make sense as as much, at least nearly as much, maybe not at all, as a strictly emergent phenomenon. It just there's not.
And also those when you get the Planck time scale, where causality gets to be quite fuzzy, literally. And if you are dealing with a process of moving forward, the sort of Zeno paradox, moving forward in motion, right? At some point you get to these Planck division of time where stuff gets to be pretty fuzzy, even though it obviously goes forward, right? So I think some of our mathematics is not quite up to scratch to understand the arrow time.
I certainly hope so.
Otherwise, it's even weirder than.
But I want to maybe push back on something that Tapio Weasel said about like causality. Like you said that causality is more fundamental. Sorry, but because I have heard from Sean Carroll that he basically says the same thing about causalities and about entropy. Like causality can only be understood in terms on the macro scale. Like on the micro scale, again, time seems symmetrical, but on the macro scale, then you can say like, oh, there's a clear cause preceding an effect, basically.
Yes. I would love to know. I love Sean Carroll. I like to say that Ben Shapiro is a dumb person's idea of what a smart person is like, and that Sean Carroll is a smart person's idea of what a smart person is like. Sean Carroll, one of the best people to listen to explain really a lot all of these ideas. Brilliant at it. He's a professor at Caltech. He has Feynman's old chair, like he has the same office and whatnot that Feynman had, and he deserves it. And he has a lot of videos on YouTube. The biggest questions in the universe is like a 26-part podcast that he did that gets into all of these things. It's fantastic. I've listened to it.
And his PhD thesis that was on the cosmological consequences of topological and geometric phenomena and field theories, right? Mm-hmm. is a really interesting thesis to dive into. If you can skip the middle if the math is inventive to you, look at essentially the statement and look at its conclusions. And it's a very interesting stuff. Again, it's consequences of topology, geometry with regards to field theories, right? See, it's a fundamental space-time stuff to quantum stuff, and he's quite a fun person, someone who understands how to say things. Because one of the things, like another famous astronomer, Alex Filipinko, is somebody who can make statements that are what we call cringe-free. They don't things where they say, it's not quite. They don't try to, like some science communicators, dumb it down to be inaccurate. He's very careful in his language, and I really appreciate it. Just like Alex Filipinko is, right? If you go to his lecture, just like Carroll's, of the stuff you know about, just to listen to how he explains it, as Feynman says, without using language of the priesthood.
Yeah, but
Real fast,
oh,
I
sorry. Go ahead.
have a question
Yeah.
to Landon. What or who made you interested in exploring this line of astronomy and stuff, cosmology?
Observation and parents that tolerated questions.
Yes. Oh my God, yes. Like what you're asking, why did you decide to become a scientist? And the answer is that curiosity was always encouraged, and the
Yeah.
world is a curious place.
Yeah. My very first sentence I spoke as a child, first complete sentence, was a question, which that's what science is. And the question, it came about, I was sitting at the dining room table at our farm in East Bay Hills, looking at the sun set over across the San Francisco Bay, over the peninsula, and seeing the sunset go down there. And I was trying to say, this is what I'm observing. I'm seeing the sun go over there. And I wanted to know, if we went over there, what would we see, right? Again, I'm less than 2 years old, so don't fault me for thinking the world might be more like a Terry Pratchett, this thing, right? But that's what I was observing, so I was asking questions. And the very first sentence I spoke as a child was, how far is the sun? Not data or anything, but how far is the sun? And so
That's
my parents went to a book. I still have the book called Questions Children Ask, and they flipped the thing because they didn't know. And there was this sign. They had a diagram of this, like one of those interstate highway signs, and it said sun, pointing up to the sun, and it was in miles, 93 million miles. And I looked at all those digits.
That's
now,
awesome, by the way.
I knew, having traveled to my grandparents' house from South Siberia up to Oregon and back, that if you're careful and you watch the odometer, you could see the thousands digit go once, right? The tens of digits there, spin, soar. And so if you spent
on the round trip
at one point. And so I knew that many digits, and I saw 93 million going well beyond what odometer did. And I was thinking, hang on, that's way too far to measure.
You're a flat earther. I knew it.
And so my second complete sentence, I asked, because again, small kids have a barrier that they don't know how to articulate. They think a lot more than what they can say. So my second complete sentence, I said, was why? Because they didn't know how to say, that number seems impossibly big. How could they actually know the sun is that far?
Wait, hold on. Did you read the 93 million miles?
Well, it's digits. You can see the numbers, right? You can see the.
Yo,
numbers.
you were 2.
I was less than 2. So
yeah, okay, you were less than 2.
You stare at an odometer, you can see the spinny thingies, and you.
Okay, yeah. Right? I guess technically you're not paying attention to digits, you're paying attention to patterns. That's still crazy. You have to keep in mind this extremely minor detail about the dashboard of the car, and then remember it over the course of a round trip distance up to Oregon and back. That's, I sir, believe that there might be a small amount of embellishment somewhere.
No, it's serious. And even to make it even more precise, I knew, I don't quite know how, I don't remember how, that a mile was 5,280 feet. And I knew that on the farm, we had the longest tape measure was 100 feet, the surveying measures, right? 100 feet, right? And so in my brain, I saw that distance and I said, sticking a tape measure out 93 million miles to the sun doesn't seem to be very practical. I didn't think that was possible.
It would fall down. They don't stand up after.
Yeah, even that thing. So it wasn't until I was 9 years old, and it was at the Morrison Planetarium in Golden Gate Park, San Francisco, where they had a planetarium show on the quest for the solar parallax. Transit of Venus and the whole thing about the voyage, the quest to measure the voyage of stuff. And and that's where the person explained how to use Newton and Halley's method to measure the distance to the sun when Venus passed in front of the thing. And he said, but unfortunately, you have to wait all the way to 2004 to observe the next one because they're rare, right?
Two things real
so I
fast.
said, okay. And I waited.
Two things real fast. One, I people don't remember this, but I remember this. How far away is the sun? 93 million miles was actually the very first $1 million question on Who Wants to Be a Millionaire back in the late 90s, early 2000s.
Really?
That was $1 million question.
The very first one, the very first ever around $1 million.
And I wonder how they got an answer because the distance to the sun is now determined there. And by the way,
There's still a best answer.
My
right?
colleague waited from 1969 to 2004 for this thing. My colleague went to Madagascar. I went to Arcetri, Italy. And the Franco Puccini, the director of the observatory, said I must not observe it at the observatory. I must go to the villa next door where the Galileo was in prison. And he was allowed by the church once a week to go on a balcony for an hour. And so we sat on the balcony of Galileo's prison and measured the distance to the sun and the fact that the Earth moved.
That's hardcore.
And then we measured 149,576,756 kilometers plus or minus 35, 42 kilometers.
And two, it's funny. It's not funny to think of, but 93 million miles or whatever kilometers is big in our minds, but in the universal thing, it's rather small.
Yeah, right?
Yeah, and it was a case, that the measurements they got from the transit of Venus was quite mind blowing, right? That those kind of distances, given that traveling halfway around the world to Tahiti was something that was kind of like going to the edge of the universe, and these things being that far. But yeah, I'm proud to be the flat earther's worst nightmare because I've actually measured distance to the sun, measured distance to the moon, and shot lasers, bounced lasers off of mirrors the Apollo astronauts left on the moon. Yes, they landed on the moon as well. Why? Because I'm still asking questions. Science values questions. So folks in the chat, get your questions. Come.
Did you have some questions about the universe according to the series you said?
I had a few questions that are like coming to me now, like over the course of the series. So one of the questions, and I probably asked this earlier though, would have been when do you think, what are the likelihoods and possibilities for when the first star formed? Like, when did that happen? Was it 100 million years after the start of the Big Bang? Was it 800 million years? Was it 2 million years? It wasn't 2 million years.
So let me give a speculation about it. If some of these notions of the earliest galaxies are when the universe had been going like 400 million years, the Big Bang process has been going like 400 million, 500 million years, somewhere around there. I mean, it's going to be plus or minus some fuzz. My speculation is that stars and galaxies formed kind of at the same time.
I would think
just but the early stars were probably much more massive because they were just mostly hydrogen, a little bit of helium. They were probably in denser environments that allowed them to be bigger and not blow themselves apart so much. Although a number of the early stars went bang quite quickly. Remember, we said the more massive the star, the shorter the life.
Yeah.
If you get a star that's like 10 times the mass, it's only lasts for millions of years rather than billions of years. So
do we have a lower bound on that, by the way? I guess keep this in the back pocket, but this question is, do we have a lower bound observationally on the lifespan of stars?
And so early on, there were probably nodules that formed again from sound. This is all the perturbations from the early universe, the sound waves, right? Sound is really big, right? Sound is what crushes a star into a black hole. Sound's what bounces off to create neutron stars,
Sound
bursts,
is-
things like that.
It is fundamentally density waves.
Yes.
And so it's going to be, a big game in town.
And the
what
fundamental
what
tone.
caused those density waves? Like, if it's isotopic, then
Quantum fluctuations.
So that's what
Oh,
you blame
alright,
on in
yeah.
quantum mechanics, right?
Yeah, when you if you sit down just very briefly, if you sit down and look at the equations of quantum mechanics, you can come up with solutions, a finite number of solutions often over a certain length scale. Just like you can only have a finite number of good tones on a guitar string. It can only have an integer or half integer number of wavelengths. And that means that there is a lumpiness that is intrinsic to the mathematics. And since the mathematics is, as far as we can tell, an excellent descriptor of reality,
Yes.
it seems intrinsic to reality.
Yeah. And so one of the things in particular for that the notion of, again, that you're saying of the mathematics being there, it is, however, the case that just because it has a mathematical formula doesn't mean the universe is doing that sort of thing. Nevertheless, in the early universe, there were sound waves whose current, the fundamental tone that appears to be going through that early hot dense universe has expanded quite a bit. The wavelength that was present when the Big Bang flash occurred, that was 378,000 years after the Big Bang process got started, has been expanded 1,100 times. So the light waves that might have been those hydrogen lines are now bound in microwave.
Yeah. And those are different waves, by the way, than the acoustic waves.
Yes. There's also these acoustic waves there, where now they're around 550
megaparsecs.
Parsecs down. They were originally down in the 500,000 on that size. But right now, if you look at the wavelength, the tone of that fundamental wave, like right now, I like to say you could calculate it to be 71 octaves below B flat. That's the of the universe, right? And it's correct.
I love it.
So why B flat? Well, because that's what the universe does, right? There was also a question about the James Webb Telescope. Did I discover anything?
That was a question. I don't know if you just answered that or not.
I just put the question in the live chat. If we
there is a thing where they've recently it's undergoing peer review, but they claim that they've detected a Lyman alpha break line. If you look at the spectrum, it's a spot where hydrogen does its thing, and that.
Do you have a link for that?
Yes, I can put it into this set here. And I'm going to put it into
we talk about Lyman alpha particles, or Lyman alpha.
In the chat, here it is, right there. It is.
Right.
So what they claim is that the redshift is 14.32, which would suggest that the light left that galaxy when the universe is the Big Bang process is only 300 million years into its process.
300. Is it the oldest discovered so far? The oldest galaxy?
That's undergoing peer review because there's things that can fool you.
And also, for the record, even if something passes peer review, does not mean it's true. It means it's not incompetent. Yes. And that's what. And you can, and we will, and you should be willing to be wrong. You're allowed to be wrong, but it means it's not incompetent.
I respect for the observers because they say this is what the data implies. We're announcing this in order to get peer review and get questions and challenges to make sure have we made a mistake, right? They're not claiming we get the record. They say, can you find a mistake in our analysis, or is this a stat? Now,
if they do say they get the record, like if you're really confident and you're right, then it ends up working out for you. It's let me tell you, how confident you should be and how unequivocal or equivocal you should be when you're in your title specifically is a conversation that I've spent hours having with my co-authors on, like, should we have this title or this title hedges a little bit more and is safer, but like we're pretty confident. We think we're right. So being a little bit more unequivocal and saying we are observing this thing.
Sadly, it's harder to get funding if you're more cautious.
Yes. It is harder.
So the normal thing to say is that some of the earliest galaxies appear to be when the universe has around 650 million years, right? Even then, that's a fast way of doing it. But I suspect we'll find there's early stars and early galaxies were kind of forming because different clumpy, lumpy bits are occurring. So I would willingly go with a half billion years as probably the time where lots of galaxies were forming. But early stars also probably formed, I'm guessing, the thing on the Eddington limit, where the more massive the star, you get to the point where the activity on the core is so violent that it blows the star apart, right?
Yeah.
And that's kind of the upper limit. Right now, the Eddington limit is somewhere in the 150 to 250 times the mass of the sun today. But the question is, back then, when you didn't have heavier elements and things were hotter and denser, could stars have gotten a little bit more of a boost? And if so, they probably were very quick to shine, reionize their universe, go bang, and have shockwaves to begin to create more rational stars. We call it irrational stars, right?
It's not a space question, but VRC wants to know if Godzilla is possible.
No. Like
not really.
I can name at least two main reasons. Like the first is of course the physiology. Like if you are so big, you are unable to support yourself under Earth's gravity. Basically, like you cannot. It's a physiology. Like you have to have like some crazy lightweight skeleton to support do that. Like basically, yeah.
What you really have to have, I think, my gut reaction would be that the biggest physics limitation, and it would be a physics limitation, would be like a fluid pressure equilibrium thing. Yeah. Because if you have, because like organisms, as we understand them, are bags of mostly water, and if they're stretched vertically over 200 feet, that is a huge differential in potential energy and pressure that needs to be really thoroughly cordoned off periodically as you go up.
Yeah.
And because if it's not, it'll just break it. Like the plumbing just won't work.
The other problem is that organism, right? You get to a size. So let's take the Terry Pratchett space turtle.
Speed of light.
Discworld is on the back of the space. I mean, the fact that physiology of nerves and the things going on that planetary scale is a big problem from the point of view of physics. But Terry Pratchett never lets physics get in the way of good humor. So thank you, Terry.
Maya says you're wrong.
Well, Maya is, all you need to know about Maya is she has horrible taste in co-hosts and therefore has no credibility on anything, right? This is a fact. It's just a fact.
Al Tucker has a question, I think, or comment.
Sure.
There's a recent announcement that they found more massive galaxies older than we thought possible to form at Enigma to the current theories about age and galaxies that form over the period of time or time period.
If you recall, when in our episode, was it episode 3, when we're talking about galaxy formation and star formation? There's probably one of the biggest hand-weaving bits, because this question about how did the first stars form, and how did the first galaxies form, and how did clusters of galaxies form, how did superclusters form, is one of the probably the biggest holes in the tail of the current Big Bang process. That's not because we're wrong. That's because that's science. That's some of the cutting edge in cosmology. And people are excited about that because
we might be wrong, and I'm sure we're wrong about these.
And that's good, because if you realize you don't know, you start testing and investigating, and you find observations. Some withstand up scrutiny, some of which are get revised. And so we're actually trying to figure it out. We're not giving you dogma that says this is what the universe is. We're trying to say we don't understand. We've heard that from us many times. So I would say an enigma is saying there's puzzling things that we're trying to fit into a model.
Yeah.
We're trying to gather data. James Webb is giving us some information. So it appears to be curious. We're going to confirm and test these things. But it sure seems like, 30 years ago, you would have said it takes a couple billion years for a big galaxy to form. That's obviously not true.
And if real fast, anybody wants to see what we talked about, there's a link to our 12-hour movie of our series.
Yeah.
You have 12 hours to spare.
Yeah. It's not true. And so how did they form? My guess is those sound waves from the early universe still were playing a role in how stars, galaxies, galaxy clusters, and superclusters were forming and arranging, all kind of at different levels. And we don't yet understand that process, but obviously it occurred.
That's one common narrative I see on the news and such. They say like, oh, the scientists have found galaxies that are too old for the cosmologists, and I say like, from my understanding, we don't even understand how galaxy formed enough to make such a judgment. Like,
Yes.
we cannot say whether galaxies are forming too fast or not. Like, we cannot say that even.
Yes, it is a very hard problem, and I think that it is fair to say that that gap between when recombination sort of finished up and when you had galaxies and stars, which I agree with Landon. I think it makes the most sense that they would have formed sort of cotemporally, because if you're going to have a dense enough thing to have a star, then it's going to be produced probably in the vicinity of something with a galaxy.
Yeah.
But
So you had eggs
that
and chickens and flocks of chickens and the whole
exactly
all at the same time.
And the speed at which that happened is, I think, still a little bit difficult, but it's not. There are bigger things in physics where people are like, wow, this really doesn't make sense. The Hubble tension would be one of them, I think.
Yeah.
Or that they have checked and double checked and triple checked and quadruple trillion checked both sides of that equation so much.
My guess, if you had to make a guess, but this is just a guess, perhaps biased because of my friends that were involved in Nobel Prize discovery, that the equations of state of the universe pre-Big Bang Flash in that recombination are not quite what we think there are, and that may have impact on our interpretation of WMAP data. It would be my guess. If I had to bet a file containing Wikipedia, that's my encyclopedia. If I had to bet that file, it would probably be that the equations of state in that early universe are not quite what we think there are, and that's enough wiggle room to fix things. But to be seen, because again, science really gets really excited when it realizes it doesn't know something, because it's learning from that. And just stay tuned.
Okay. I have a question. I think we talked about a little bit in our. I think either episode 2 or before Earth 2 or before Earth 3 show. What's the difference between a population of 1, 2, and 3 star?
Population 3 is the oldest. They are named because in the order that they were discovered. Population 1 is the newest and closest and most obvious, and then population 2 is a lot further away. And so they were discovered second, and then population 3. I don't know that population 3 has been definitively detected.
But there are metal poor stars. That
we don't have like a prototypical poster child example of one yet. I don't. Well,
Yeah.
and I don't know
Yeah,
if
they're
we'll ever
not
have one
very
from
convenient.
one because they're so far away. But
Yeah.
necessarily by construction, and necessity of how we think, the past happened, they are going to be, in the ballpark of 13.5 billion light years away.
Yeah. So the
And
new
actually more than that because,
the
expansion.
new European Space Telescope, combined with Theo Rubin, I have a colleague who's really big on looking at brown dwarfs. Because she's saying if you're going to find one of those ancient stars, it might be a star that's barely fusing, that's been sitting around for a long time, captured as our galaxy did mergers and acquisitions. And you might find one of those brown dwarfs being one of the really ancient ones.
Could be.
There with fairly pure hydrogen, helium, traces of lithium.
Well, would it still be pure?
Wait, what's gonna shove stuff into it at any appreciable rate?
It could have. See, if it's been around, so I could totally imagine that happening as sort of like one of the little like clumps of stuff that gets ejected during the collapse of what we typically think of as big, the big first stars that flamed out after 10 million years because physics. But in that case, I could totally imagine that it would still be exposed to and accrete a fair amount of metal.
But stars tend to not acquire stuff; they tend to lose stuff unless they're got a companion shoving in. So
but would they tend to acquire
sitting out there minding its own business? Most stars don't encounter other stars.
You're right, but metals are going to behave differently ballistically than hydrogen and helium, right? So metals, if you have a star, a dwarf, like a brown dwarf, going through a cloud of high metallicity, the even a negligible amount of solar wind, and if we're talking about brown dwarfs, and even that's kind of a sliding scale of a question, is going to push a lot of it away. But I'm not sure if it does it with the metals.
And I'm sure it's going to be, but it's going to be pure. I don't know how fast it would acquire enough mass to say, hey, that thing. So it might not be ultra pure, but it will be metal poor. That is poor in anything other than hydrogen, helium, with a trace of lithium. And
that's true.
And so they're looking for nearby population 3 stars amongst what brown dwarf is going to be in the infrared and stuff. So
I guess
they're saying let's try that because if we find stuff way out there, it's harder to look at versus stuff.
No, for sure. If you find an extremely metal poor brown dwarf locally, that would, I mean, I didn't even consider that. Like that didn't even I didn't even consider that as a possibility. It would be extremely illuminating. Well, not really, because it's a brown dwarf.
Pun intended. But yeah, she's a pretty smart thing. So I wish her luck, and she's got time on telescopes to begin looking for these surveys of really faint. These are things that are not stars because they're fusing, but they have a lifespan of trillions of years, and they're just sitting out there minding their own business, doing their thing from when they started early on. And there's no reason to think that every star that in the early Big Bang process had to be massive, right? There's probably small things.
Exactly, especially as the offshoot sort of clumps of maybe a bigger process. You're going to get that. You're going to, because turbulence is a thing.
Ness says apparently some people think old galaxies disproved the Big Bang.
That's something I said before. Yeah, like if you the discoveries of very old, distant galaxies, and they say like, oh, that's too early for the Big Bang for some reason. Like I don't know about that. Yeah,
and that makes as much sense as saying whales disprove biological evolution, right?
The problem, I think the problem fundamentally comes from the fact that scientists are, like everybody else does, using language that is going to attract attention without Yeah, they're hyping it up. When scientists say this really is going to make us rethink, they mean in the way that a scientist does, where they're like, "Oh, that thing that we thought we had settled like 5 years ago in that big argument when we were all at the bar or something. Like now we're actually going to revisit that because I remember that guy thought that one particular thing, and I did the experiment, and look what happened." Okay, not like, "Oh my God, atoms don't exist." These people think atoms don't exist. In the analogy. Okay, I'm done. Sorry. I got excited.
The question is, could JWST detect all the stars, or would it just be limited to luminous galaxies?
We found some very old stars in the process of looking at gravitational lensing arcs. When a massless object focuses light and concentrates light from farther back. And we found, I think that star is called Methuselah. We found some very old stars that way. And
by the way, that when Landon says we, are you referring to something that you personally were on the team that did this, or are you referring to something?
I will not say that I peer reviewed a paper, because that would be telling.
Okay. Okay, so Landon totally did not probably maybe peer review a paper that this happened in. So he didn't write the paper, but he also totally probably didn't peer review it.
Yeah. But back to saying, one of the things is that the Webb telescope is not a survey telescope. Vera Rubin, frequent 2 degrees, which is a huge field, that's a survey telescope. Webb is really tiny spots, and so you're not going to scan the entire sky with Webb. It won't last that long.
Totally different instruments.
So it's a needle in the haystack sort of thing where you can look at stuff really carefully, and so you got to find it. So people are, hey, those Einsteinian rings. When we've seen the distorted stuff, let's scan along the ring to see if we can find stars. We found out, yeah, we can. We actually can find interval stars that are fairly, that are fairly, far away, that started when the universe was relatively young, and so we're getting good data from there, because it's not just there's a dot. You didn't want to get spectrum, and you want to try using something like ALMA in radio telescope stuff to study things. You got to try to multiple. You got to do more than just say there's a dot. Say what's interesting about that dot, what's its characteristic, is it polarized? Can we see it in different wavelengths? Is there other stuff that could be happening there? Those are all the things you tend to try to figure out once you detect you might have a dot. Just like this galaxy, if it holds up the peer review, it's going to be because there's other things that are going to look at it in different ways, and the Webb will probably spend more time looking at it, and maybe Hubble as well.
We're waiting for final questions. Anything you guys want to advertise coming up?
There is the volcano show that's going up on Chess's channel. I believe the volcano show is. I'll find it here. Chess is probably saying, "Landon, I told you," but I don't know. Volcano show July 5th, starting at I believe it's 13:30 Pacific, 1:30 p.m. Pacific on July 5th. We're going to see just how wrong we were about Pele. Madame Pele had an 11-hour eruption when we thought it wasn't going to erupt, and then I predicted it was going to erupt again, and so far it hasn't. So Madame Pele continues to make predictions and trash them. So come and see how wrong we are. But we also have learned some stuff. Like when the volcano does things, we say, "Oh, that's what happened. Okay, we didn't know that." So we learned something. So come to the show, learn something about volcanoes, and if Pele is erupting, we'll show you what we call volcano porn, lava.
Sometimes Mother Earth squirts.
It's going to be very hot.
Yes.
In more senses than one.
Today.
So I question, or comment rather, not a question. Landon, why would you do this? Okay, getting into specific predictive science about geophysical systems like volcanoes is the equivalent of invading Russia in the winter. Okay, it's a terrible idea.
Yeah.
That is the hardest thing to do.
Part of the thing we try to do is to show how little we know about volcanoes, right? And what happens at the end of the show is the hosts make their guesses, people on the chat make their guesses, and we review stuff and say, well, this is what happened, and then we say, okay, we missed this. Why do we mess up here? What do we not know? Right?
I would refuse to give an answer. If I were on the panel, I'd be like, I'm not answering that question. This is a trap.
Yes. So, and we laugh at each other, laugh at how wrong we are. And the next thing, because it's
I wouldn't be
it's
wrong.
An interesting process, but it is we learn some stuff, and sometimes people nail it. There was somebody who nailed the last thing, but that's more matter of guessing, right? But still, the
Probably.
what we're stating is plausible, but the ability to, it's like saying the ability to predict the weather exactly to a very precise level a month from now is nil. On the other hand, you can say in this hemisphere we're going towards summer, so it might be generally warmer, right?
But
you can do those sort of
predictions. How far in advance were your predictions made?
1 month.
Oh God! What? That's just random at that point.
Yeah, but we get fun. You can fun laughing at us on how wrong we are. But then we analyze. But the other thing is,
I would just always predict nothing would happen.
Is we spend most of the show is spent looking at telemetry and saying, here's this data, and looking at this tilt meter, and looking at this gas meter, and blah 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 blah. And so what we do is say, given this telemetry, this might be a most likely outcome. But we're sometimes surprised, sometimes not. It's a fun thing. But people who watch the show begin to get a sense of the rhythm and patterns the volcano is making, so that when stuff happens, you get a more appreciation for these volcanoes are not so just random, right? There are things happening. It's just that there's too many hidden variables underground, literally. So,
time out. Are you saying that the volcanoes have chakras? Because it sounded like you were saying that the volcanoes had chakras. Okay, and
no. There are patterns, and there are events. We look at telemetry to see things and stuff we know. And then you learn often after the fact the data. We understand certain sensors that are leading indicators, certain sensors that are trailing indicators. And so you begin to see the pattern stuff. Yeah. And so, but then we just throw caution to the wind and make a guess and then laugh at how wrong we are.
Fair enough. As long as like the state of Hawaii isn't like relying on you to send out text messages to all its people. If they were doing that,
what they do rely on is the sensor data. So we went there to look at stuff. It was we thought we were having a major rift eruption to get the sensors in place to advise the civil authorities of what happened, but it turned out eruption lasted only 11 hours, and by the time they got there to put sensors, the eruption stopped. But that happens, right? You look, and so we go back and look at the history of the volcano. It has short eruptions and long eruptions, kind of in between there. So you learn about telemetry, you learn about patterns volcano makes, you learn about observations, you learn about results, and so we have a better idea about what happened, why that 11-hour eruption occurred. It wasn't we originally thought it was. It wasn't the big rift eruption. It was a different sort of thing. And so because when we make mistakes, we say, okay, the mistake was made. What do we miss? Look at this data. That's interesting. And so we learn. So come with us to learn about there, and you will then get an idea about stuff that when a volcano does erupt, you say, yeah, that seems to be possible given the da, right? So yeah, it's a fun deal.
I did have a question, by the way, before we wrapped up. This is a much more straightforward technical question that I could Google. How so Proxima Centauri is something like 3.5 or 4 light years away, something like that, whatever. How many AU is that? How many astronomical units?
You're talking about isn't it
Well-
3.4 light years? Is that the
Something like that. How many like light years to an astronomical unit? Do you happen to know off the top of your head?
I can do the calculation here. 3.4 light years is in AU. Is going to be 215,000 AU.
Okay.
Is it 3.4 or is it 4.3? Maybe it's 4.3.
I don't know. Like how many light years how many AU per light year would be a more informative, that's the teach a man to fish answer, right? Is how many
and I think because Alpha Centauri I thought was the distance was 4.3 light years, isn't that right? Isn't the distance? 4.3 light years. 4.3, and Alpha Centauri's are there. So 4.3 light years is approximately 272,000 AU. 272,000 AU.
So if we divide 272,000 divided by 4.3, then we get a conversion factor.
60,250. 63,250. Excuse me, about 63,250.
Okay, so 63,000 AU per light year, roughly.
Yeah, and that sort of thing.
So Tapioca,
and so the outer Oort cloud is of a light year, right?
Yeah, I think it's like 0.5 or 0.3, or it depends on which paper you read.
It depends on how
loose idea.
Stuff. So how do you think like these are stars that get to the point of near 1 light year? You have a lot of perturbation of stuff that causing all kinds of higgly-piggly stuff happen to occur in the outer regions where stuff is so tenuous on sun's graph that another star can go yank.
So Tapioca, do you want to advertise a certain show you might be doing tomorrow with a certain Maya person?
I mean, given the way she's been bad mouthing me in chat, I'm not sure I do. I'm just kidding. Okay, so tomorrow we're going to be on Bad Science Sunday, and we are going to have the fantastic, inestimable, Dr. Dan Stern Cardinal from Creation Myths. We're going to have Dr. Dan Stern Cardinal from Creation Myths on our show tomorrow, and it's going to be fucking awesome. Sorry.
And so just the bad science there. Describe the
channel.
So
tomorrow so Bad Science Sunday over on Maya Adkisson's channel. We do it every Sunday at 9:30 Eastern, 6:30 Central PM on Sundays because it's Bad Science Sunday, and it's Maya and myself. Her co-host, that's a choice. Me, there's that. But and we react to it's often science, it's not actually always science. And tomorrow we're going to be reacting to a video from a Christian channel where they're like, the evidence very clearly shows that creation is a better model than evolution, which,
Are they going to explain the Noah's flood heat problem?
No, no. Well, I mean, we can explain it, but they can't explain it. Nobody can explain it on their side, right? Like,
sure.
As for me, coming this Wednesday, special Wednesday episode, me and my guest, Eric, Snick, and Jillian, we talking about the different eras of animated Disney movies, why they're called the Golden Era, the Bronze Era, the Dark Age of Disney movies, the Renaissance, and now the streaming era of Disney movies. Was
Frozen in the Renaissance?
No, Frozen is in the revival. It's called the revival era.
Okay, because I mean, Frozen is going to go down a hit. Frozen's fantastic. I'm just saying.
Yeah, the Renaissance died in 90. The Renaissance was over in 99. Frozen's way after 99.
Yeah. Okay.
Although I do have an opinion. I think Tangled is better than Frozen.
But yeah, apparently there's two Dark Ages now. The Dark Ages before stars were formed in the universe, and the Dark Age of Disney movies in the early 80s.
And the dark ages of what happened to the Star Wars franchise. Did I say that? I didn't say that. But thank you so much, folks, for watching us make mistakes, watching us explain things that we don't know about. And if you find mistakes, investigate them. Don't think what we said was the gospel truth. And we've tried to refine ourselves and give you a notion of the curiosity of this amazing universe.
Yeah, what people may think we are not the popes of YouTube.
And understand, a lot of stuff we skipped over. We didn't spend 13.78 billion years detailing everything that happened.
I've talked to people who I asked, for my personal life to watch the show, and they confirmed that, yeah, it did feel like that. But that's because they were just listening to me. Be polite.
But seriously, I think you saw a bunch of stuff there, wonder about this process, and hopefully when you see another article about something in science where maybe they do something at CERN, maybe the Webb pulls out something, or the new Gaia telescope pulls out something, or the new European telescope. I forget what's the name of it. You know the new big telescope that they put out there? I'm trying to remember its name now. When you see stuff happening, you have a context to put it in, right? And understand that 100 years from now, they'll look at what we were saying and say, ha ha ha, they didn't know about blah 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 blah. They won't say ha ha, but they'll look at our stuff and say, well, that's what they thought.
Were you thinking of WISE? Was that the telescope you were thinking of?
Is that the new one?
I don't know if it's new, but I
thought WISE was an old one. There's a new European Space Telescope.
Oh, I don't know if new European Space Telescope.
Well, before we go, I just want to say thanks everybody for watching. Want to help support the channel? I have a wish list below, and Patreon and all this stuff. But if you can't support it, just simply liking the video and sharing it around. We'll get the YouTube algorithm.
I want to clarify the comment also from me that's on screen. I was reacting to something Maya said. Okay, I am not that level of elitist. Okay, I'm elitist in that if you think the Earth is flat, I'm not really going to pay attention to your other opinions scientifically.
Yes.
But that is like 8 orders of magnitude from Landon is an astronomer. I am not an astronomer.
But he's a physicist, and that's also done. And
it's related.
By the way, the telescope's called Euclid. Look up the Euclid telescope.
That's a hilarious name.
The dark universe.
Because, if you're using lensing ever, it's basically just a middle finger to Euclid. Okay.
And as always, never stop learning and enjoy the randomness.
Please.
I don't know if we'll see you. All of us will be together again in the future, but if we are, we'll see you next time.
Tomorrow night, Bad Science Sunday. Be there.
Bye.